Welcome to Spring LIB.
Now, to start on this question, we need to first identify what is the total amount of energy that the body uh, can absorb, right? That's given by the limit 50 millirem, right? To find the total energy, and subsequently, with the total energy, we can find the total number of nuclei that can be present, because we are given that each nuclei would emit 140 keV gamma rays, right? So from there we can tell, or we can infer what is the maximum number of nuclei that can be in the patient, and then from there we can find the initial activity, right, based on this total number of nuclei. So first off, total energy that can be absorbed. We know that 50 millirem is equals to the dose multiplied by the RBE factor. But in this case, we are dealing with gamma, so the RBE factor is 1. So 50 millirem is equals to 50 millirads. Alright. And we know that one rad is equals to, 100 rad is equals to 1 joule per kg. So what we have to do is we divide that by 100 to give us in terms of joules per kg. Then we multiply this by the mass of our patient, which is 55 kilograms. And then because it is now in terms of joules, it would be better if you can convert it into electron volts, since the energy of our gamma rays is in terms of electron volts. So to convert that, we actually divide by 1.6 times 10 to the power of minus 19 joules per EV. And we should get a value of 1.719 times 10 to the power of 17 EV. So this is the total energy that can be absorbed by our patient. Now the next thing that we need to do is to find what is the total number of nuclei. Now we're given that half of the gamma photons don't interact with anything, so the total gamma rays that can be emitted by the sample would be equals to 1.719 times 10 to the power 17 divided by 140 times 10 to the power 3 EV, and multiply this by 2, right? Because this is the number of gamma absorbed, but we are given that only half of the total gamma rays will be absorbed, right? So this is the total, multiplying by 2, we get the total gamma rays emitted by the sample. And the total number of gamma rays is equals to the total number of nuclei, since each nuclei will emit one gamma ray, and so we get 2.455 times 10 to the power of 12, right? So which is also equals to the number of nuclei. So given that this is the total number of nuclei, we can find what is the total initial activity. So the initial activity is given as lambda multiplied by n, where lambda is the decay constant. To find the decay constant, we take ln 2 over t half, right, where t half is given as 6 hours, right? So 6 hours, that is 6. But in terms of seconds, right, because we want our activity to be in terms of SI units, which is either in becquerels or in curies, right? We convert this into seconds. That is 3,600 seconds per hour. We should get our value in terms of decays per second. Right, so 1 point. Should get 7.877 times 10 to the power of 7 decays per second. Or if you would like, you can convert it into curies by dividing by 3.7 times 10 to the power of 10. Right, this is the number of decays per second for each curie, and we should get 2.129 times 10 to the power of minus 3 curies, or 2.13 millicuries, right?